February 1943. North Africa. German tank crews had just fought one of their most intense battles against American forces. When the dust settled at Sidi Bou Zid in Tunisia, among the wreckage and abandoned equipment, German reconnaissance units found something extraordinary. An M4A1 Sherman tank, completely intact, sitting there like a gift waiting to be unwrapped. The tank still had its American star painted on the side, and someone had scrawled War Daddy 2 on the hull in white letters. What happened next would shake German confidence to its core. This wasn't just another captured enemy tank to be photographed and forgotten. This was about to become the most thoroughly examined piece of American equipment the Germans would study during the entire war. And what they discovered would haunt their engineering departments for years to come. The German officers who found this Sherman didn't just drive it back to their base. They drove it 350 kilometers across brutal North African terrain to the port of Sfax. 4.5 days of continuous driving through sand, rocks, and scorching heat. Their own tanks regularly broke down on journeys half that distance. But this American tank, it just kept going. The engine didn't overheat. The transmission didn't fail. Nothing broke. German mechanics traveling with the tank kept waiting for something to go wrong, but it never did. That journey alone should have told them everything they needed to know. But the German army wanted answers, real answers backed by scientific testing. So they loaded War Daddy 2 onto a cargo ship bound for Germany. Destination: Kummersdorf Proving Ground, 25 kilometers south of Berlin. This facility was where Germany tested all of its most important military equipment. It had the best engineers, the most sophisticated testing equipment, and a reputation for brutal honesty in technical assessments. When the Sherman arrived in spring 1943, it was immediately given a German designation, Panzerkampfwagen M4748A, along with license plate WH058941. Engineers swarmed over it like scientists examining an alien spacecraft. They measured every angle of armor. They photographed every component from dozens of perspectives. They documented construction techniques that seemed impossibly simple compared to German methods. But it was when they started looking inside that things got really interesting. The transmission caught everyone's attention immediately. German tanks used straight-cut gears, which required incredibly precise manufacturing and constant maintenance. These gears were strong but temperamental. If they weren't perfectly aligned, they'd wear out fast or break completely. The Sherman used something called herringbone cut gears. These gears distributed stress across multiple teeth at once, making them far more durable and much more forgiving of small imperfections in manufacturing. The German engineers stared at this transmission in disbelief. Herringbone gears had been standard in American car manufacturing since the 1930s. American car companies had been making these by the thousands every single day for over a decade. Meanwhile, German engineers had dismissed herringbone gears as too difficult to mass produce. The Americans hadn't just figured out how to make them in quantity. They'd made it look easy. The testing began in earnest. Engineers drove the Sherman through obstacle courses designed to break vehicles. They measured fuel consumption down to the milliliter. They monitored engine temperature constantly. They recorded how the transmission behaved under every conceivable condition. After each test, they took components apart to look for wear patterns, checking for any sign of weakness or poor design. The results contradicted everything German tank doctrine had taught. The Sherman wasn't the fastest tank. It didn't have the thickest armor or the most powerful gun. But it did something German tanks consistently failed to do. It just worked. Test after test, day after day, the Sherman performed adequately in every category and excelled in the one metric that actually mattered most for winning a war. It kept running without needing constant repairs. Let's talk about that transmission in more detail because it reveals something fundamental about how Americans and Germans approached tank design differently. The Sherman had 5 forward gears plus 1 reverse. Gears 2 through 5 were synchronized, which meant drivers didn't need to use a complicated technique called double clutching during normal operations. If you've ever driven an old car or truck without synchronized gears, you know how tricky it can be. You have to press the clutch, shift to neutral, release the clutch, rev the engine to match the speed of the next gear, press the clutch again, then shift into the next gear. Miss any of these steps and you'll grind the gears or damage the transmission. German tank transmissions required this double clutching technique for almost every gear change. Tank drivers needed extensive training just to learn how to shift gears properly without destroying the transmission. It took skill, practice, and constant attention. The Sherman? You could teach someone to drive it in a few hours if they'd ever driven a regular car. The Americans designed their tank to be operated by ordinary soldiers with basic driving knowledge. The Germans designed their tanks assuming highly trained specialists would always be available. Think about what this means in a real war. America could take a factory worker who'd driven a Ford truck and turn him into a tank driver in a matter of days. Germany needed to spend weeks or months training each driver to handle their temperamental transmissions. When drivers got killed or wounded, which happened constantly in combat, America could quickly train replacements. Germany struggled to find people with the necessary skills. The Continental R975 radial engine in War Daddy 2 impressed the German engineers for different reasons. This engine had started life as an aircraft engine before being adapted for tank use. It maintained consistent power across temperature ranges that would have caused German engines to overheat or lose significant power. The cooling system was beautifully simple but highly effective. The air filtration system handled desert sand without the constant clogging problems that plagued German tanks in North Africa. Everything about the Sherman reflected a design philosophy that put practical functionality ahead of theoretical perfection. German engineers loved to optimize everything on paper, calculating the theoretically perfect specification for each component. American engineers built things that worked reliably under the messy, unpredictable conditions of actual combat. In June 1943, something remarkable happened. Albert Speer, who was in charge of all German armaments production and reported directly to Hitler, came to watch a demonstration at Hillersleben artillery range. This wasn't a small event. Senior officers from across the Wehrmacht attended. Leaders from Germany's biggest industrial companies were there. They were going to see Germany's latest and best tanks compared directly with captured Allied equipment. War Daddy 2 sat next to a brand new Panther tank fresh from the factory and a Ferdinand tank destroyer, which represented Germany's most advanced armored vehicle technology. The test was simple: climb a steep hill. The Sherman went first. Its driver shifted smoothly through the gears, the engine maintaining steady power, and it climbed the slope without any drama whatsoever. The driver made it look easy because it was easy. The Panther went next. Its 700 horsepower Maybach engine was significantly more powerful than the Sherman's 400 horsepower radial. But even with that extra power, the Panther struggled noticeably more than the Sherman had. Then came the Ferdinand's turn. This 65-ton monster with its sophisticated electric transmission system stalled halfway up the slope. In front of Speer. In front of dozens of senior officers. In front of industrial leaders who'd come to see German technological superiority demonstrated. The recovery crews had to restart it multiple times, each failure more embarrassing than the last. Speer wrote about Sherman capabilities in his memoirs years later. He noted that reports on the cross-country mobility of the Sherman had been very favorable, with the tank climbing mountains German tank experts had considered impossible for tanks. He specifically mentioned that the 26th Panzer Division had reported the Sherman's mobility advantage. This wasn't just one engineer's opinion. This was Germany's armaments minister, the man personally responsible to Hitler for weapons production, publicly acknowledging American superiority. On June 27, 1943, an article appeared in Das Reich newspaper, a major German publication. It described the Sherman as one of the special accomplishments of North American laboratories and called it quite a praiseworthy product of the North American steel industry. The article mentioned the Sherman's Euro-stabilized gun as the first attempt of its kind ever made anywhere. Even German propaganda couldn't completely hide the truth. American tanks weren't just adequate. They were in many ways better engineered than German tanks. Back at Kummersdorf, the testing continued through summer and autumn of 1943. Engineers pushed the Sherman to its limits, conducting extended trials that revealed its true operational capability. They documented operational ranges exceeding 2,000 kilometers before major maintenance was required. Let that sink in for a moment. 2,000 kilometers. Early model Panthers, Germany's premier medium tank, could barely manage 500 kilometers before requiring major repairs. The Sherman could go 4 times farther. The transmission efficiency measurements showed something equally remarkable. Power losses through the Sherman's drivetrain were significantly lower than any comparable German system. This meant more of the engine's power actually reached the tracks to move the tank, rather than being wasted as heat and friction in the transmission. The synchronized manual transmission made gear changes smooth and simple, with no need for the careful rev matching and double clutching that German systems demanded. Then there were the final drives. These are the gearing systems at each end of the tank that transmit power from the transmission to the tracks. They're subject to enormous stress, especially in heavy vehicles. German Panther tanks used final drive systems that had been inherited from Tiger tank designs. These systems used straight-cut gears and housings that simply weren't strong enough for the loads a 45-ton Panther imposed on them. German mechanics in North Africa and on the Eastern Front reported Panthers breaking their final drives and being abandoned after movements of less than 100 kilometers. The Sherman's final drives used the same herringbone gear principles as its transmission. They rarely failed, even under sustained combat conditions that would destroy German components. Decades later, when restoration projects examined Shermans that had been sitting in storage for years, they found final drives that needed no mechanical restoration at all. The Americans had built these components with design margins that exceeded requirements by such large factors that even years of neglect couldn't hurt them. By late 1943, Kummersdorf had generated comprehensive internal reports that painted a sobering picture for anyone willing to look at the data honestly. The Sherman demonstrated American automotive engineering maturity that Germany fundamentally lacked despite all its theoretical knowledge and scientific expertise. American mass production techniques allowed tolerances that German precision manufacturing would have considered sloppy, yet these supposedly crude American methods resulted in more reliable vehicles that functioned better under field conditions. The entire design philosophy was different. American engineers prioritized keeping vehicles operational in combat. German engineers prioritized achieving theoretical performance maximums that looked impressive in specification sheets but couldn't be maintained outside of controlled testing conditions. American tanks used interchangeable parts that could be swapped using basic tools and minimal training. German tanks required factory-level precision and specialized equipment for many repairs. Here's something that really explains the difference between American and German approaches. Before the war, car ownership in the United States was widespread. Ordinary Americans from all economic classes owned automobiles. Mechanics who could fix cars were everywhere. The automobile industry had matured through decades of commercial competition, learning hard lessons about what worked reliably and what didn't. Germany had far more limited civilian automotive experience. Cars remained luxury items for wealthy people and party elites. The Volkswagen program that Hitler had promised German workers since 1934 had delivered fewer than 1,000 civilian vehicles by 1939. When war started, Germany simply didn't have the same depth of automotive knowledge that came from millions of people driving, maintaining, and repairing cars every day. This difference translated directly into tank design. Americans built tanks that mechanics with civilian automotive training could maintain using skills they already had. Germans built tanks that required specialist training and constant expert attention from personnel with years of specific military technical education. Think about the implications. America could pull a mechanic from a car repair shop and have him fixing tanks within weeks. Germany needed to train specialists from scratch, a process that took far longer. The Panther tank provides a perfect example of how this played out. Panthers required strict operational restrictions to prevent mechanical failures. Field manuals explicitly warned drivers not to change gears frequently because excessive shifting damaged the transmission. Third gear in particular broke so often that drivers were instructed to avoid using it except when absolutely necessary. Panthers could not turn while backing up because this would destroy the transmission. Pivot turns, a basic maneuver for any tank, were only possible when ground resistance was equal on both tracks, which severely limited tactical flexibility. Foreign objects entering the running gear could jam the drive sprocket, requiring hours of maintenance work to clear. These problems existed despite Panthers being built in dedicated tank factories by skilled German workers using the best materials Germany could provide. Meanwhile, the Sherman had been designed by automotive engineers at General Motors, Ford, and Chrysler, applying mass production principles they developed over decades of making civilian vehicles. The Sherman used commercial automotive components wherever possible, leveraging existing supply chains and manufacturing expertise that had nothing to do with military production. The transmission came from multiple manufacturers including Caterpillar Tractor, Buick, and Ford Motor Company. All of them built to identical specifications with fully interchangeable parts that could be mixed freely without any adjustment needed. You could take a transmission from a Buick-built Sherman and install it in a Ford-built Sherman without changing anything. This level of standardization was completely routine in American automotive industry but remained largely theoretical in German tank production, where each manufacturer introduced subtle variations that prevented true parts interchangeability. More captured Shermans arrived at Kummersdorf through 1943 and 1944. Some came from British units in Italy. Others came from Soviet forces on the Eastern Front who'd received them through Lend-Lease. Each captured vehicle underwent similar testing, building a comprehensive database of American tank capabilities. The British had modified some Shermans by installing their 17-pounder anti-tank gun, creating what they called the Firefly variant. This gun was much more powerful than the standard Sherman 75mm gun and could destroy any German tank from the front. German engineers examined these Firefly Shermans with particular interest. The large turret ring on the standard Sherman had accommodated the significantly bigger 17-pounder gun with only minimal modifications. This demonstrated growth potential built into the original design that German engineers hadn't even considered. The Panther, which had been rushed into production to counter Soviet T-34 tanks, had no capacity for significant armament upgrades without complete redesign of the turret and vehicle. The Sherman could be upgraded in the field. The Panther was locked into its original configuration. The automotive testing program expanded to include reliability trials specifically designed to replicate combat conditions as closely as possible. Engineers drove Shermans through hundreds of kilometers of cross-country movement, recording every mechanical incident, every maintenance requirement, every component failure. They compared these results with field reports coming back from Panther and Tiger units operating on the Eastern and Italian fronts. The numbers told a story that was impossible to ignore if you looked at it objectively. Panther operational readiness averaged below 40% through most of 1943. Some units reported catastrophic rates as low as 20 to 25% operational. Think about what this means. Individual Panther battalions sometimes had periods when fewer than one tank in 5 was actually capable of combat operations. The other 75 to 80% were broken down waiting for parts or undergoing repairs. Sherman tanks maintained substantially higher operational availability across all theaters. Specific data from German field reports documented the Panther reliability disaster in devastating detail. In July 1943, during Operation Citadel at Kursk, Panthers achieved only 16% operational readiness. Mechanical failures eliminated more tanks than Soviet guns did. By December 1943, readiness had improved to only 37%. February 1944 showed 37% operational. April 1944 reached 50%. May 1944 finally achieved 78%. Look at that progression. It took nearly a year to get Panthers to a 78% operational rate, and that was considered a major success worth celebrating in German military communications. Shermans had achieved better than 78% operational readiness from initial production in 1942. The Germans spent a year of desperate effort to reach a standard the Americans had exceeded from day one. Engine lifespan comparisons were equally brutal. Sherman diesel variants exceeded 3,000 kilometers under proper maintenance. Panther engines barely reached 1,000 kilometers even after improvements had addressed the worst early problems. A German report from March 1944 proudly announced that improved Panther engines now achieved service life of 700 to 1,000 kilometers. They presented this as a victory. But it meant Panther engines were lasting roughly one-third as long as Sherman diesel engines. Sherman transmissions required minimal maintenance between overhauls, with synchronized gears making driver error less likely to cause damage. Panther transmissions demanded constant attention and frequent repair. That problematic third gear became so notorious that experienced drivers learned to skip from second gear directly to fourth gear to avoid using the ratio that kept breaking. Imagine being a tank driver and having to remember not to use one of your gears because it might break at a critical moment. Sherman final drives operated reliably under conditions that routinely destroyed Panther final drives within 100 to 200 kilometers. Field reports from German units using captured Shermans reinforced everything the Kummersdorf testing had shown. German mechanized units, desperate for reliable vehicles as their own equipment degraded, eagerly used any captured American tanks they could obtain intact. Unlike Soviet T-34 tanks, which Germans extensively modified before using, Shermans entered German service without changes. They didn't require modification because they worked correctly as designed. German tank crews who had experienced multiple mechanical failures in their own vehicles found the Sherman's reliability remarkable. Reports from panzer regiments noted that Sherman operators could focus on tactical considerations and combat effectiveness. Panther and Tiger crews, by contrast, constantly worried about reaching the battlefield without a breakdown or completing missions before mechanical failure left them stranded. Let me tell you about a specific example that really drives this point home. The 10th SS Panzer Division captured 12 M4A3 Shermans at Herrlisheim in January 1945 during Operation Nordwind. These tanks had belonged to the American 43rd Tank Battalion and were captured intact when their crews abandoned them during the German assault. The 12 Shermans were formed into the 13th Company of the 10th SS Panzer Regiment and served in combat operations for the remainder of the war. These German units used the captured Shermans primarily as reconnaissance vehicles and mobile reserves. Both roles required sustained movement without maintenance stops and absolutely reliable mechanical performance. German commanders had learned what Kummersdorf testing had proven years earlier. American tanks could be counted on to function when needed. This dependability, more than firepower or armor protection, determined their tactical value in the final months of the war. A Sherman arriving at the battlefield with an operational gun was infinitely more useful than a Panther with superior firepower, broken down 20 kilometers behind the lines. January 1944 brought expanded testing as more equipment reached Kummersdorf. Engineers examined the M4A1 with its Continental R975 radial engine, documenting characteristics and comparing it to other variants. They tested the M4A2 with twin General Motors 6046 diesel engines, noting superior fuel efficiency. They evaluated the M4A3 with the Ford GAA V8 gasoline engine, which American crews considered the best Sherman power plant. Every variant demonstrated the same fundamental characteristic: excellent automotive reliability derived from sound engineering principles and quality manufacturing. The diesel-powered M4A2 particularly impressed German engineers. Soviet forces received 4,102 of these tanks through Lend-Lease, and significant numbers fell into German hands during Eastern Front battles. The twin GM 6046 diesel engine provided performance matching any Sherman variant while consuming substantially less fuel than gasoline engines. This was a critical advantage as German fuel supplies dwindled throughout the war. German designers had experimented with diesel tank engines but abandoned the effort due to manufacturing difficulties and complexity of fuel injection systems. American industry produced diesel Shermans alongside gasoline variants without disrupting production schedules. This demonstrated manufacturing flexibility and technological sophistication that German industry never achieved during wartime. March 1944 brought reports from General Heinz Guderian, Inspector General of Panzer Troops. He noted in official communications that improvements to Panther reliability had achieved what he termed acceptable standards by early 1944. Engine life had reached 700 to 1,000 kilometers, and final drive problems had been largely resolved through design modifications and improved manufacturing. Guderian presented this as significant success in German military communications. But look at what this really meant. Germany had spent over a year of desperate effort, consumed enormous resources, diverted skilled workers from other projects, and finally achieved reliability standards that Sherman had exceeded from initial production in 1942. The German army was celebrating reaching a level of performance that American tanks had surpassed 2 years earlier. This wasn't victory. This was admission of how far behind German development had fallen. The comparison grew more painful as German tank production struggled with increasing resource shortages and Allied strategic bombing. Allied bombing campaigns targeted key bottlenecks in Panther and Tiger production chains with increasing effectiveness. The Maybach engine plant in Friedrichshafen suffered severe damage from Royal Air Force Bomber Command on the night of April 27 to 28, 1944. The raid involved 322 aircraft, and archives describe it as the most damaging raid on German tank production of the entire war. The attack also destroyed the ZF gearbox factory adjacent to the engine plant. Production of tank engines and transmissions halted completely for 6 months. When production finally resumed in November 1944, quality control had degraded significantly. Slave labor, increasingly employed in German tank factories as German workers were conscripted for military service, introduced deliberate sabotage. Workers jammed cigarette filters in oil passages. They installed gaskets incorrectly. They assembled components without proper clearances. These problems never affected Sherman production. American factories sat safely in the United States, far from any combat zone, staffed by motivated workers earning good wages under decent conditions. There was no strategic bombing of Detroit. There was no sabotage by forced laborers. There were no desperate shortages of critical materials. American industry could focus entirely on refining production and improving quality, rather than simply trying to keep factories running under constant attack. The fundamental difference between American and German tank production wasn't about engineering knowledge. German engineers understood automotive principles as well as their American counterparts. They possessed extensive theoretical knowledge and scientific expertise. They simply never applied those principles consistently to tank design, instead prioritizing other factors that seemed more important at the time. German tanks emphasized performance characteristics that made for impressive specifications but resulted in poor reliability under field conditions. The Panther's powerful 75mm KWK-42 gun and thick frontal armor came at the cost of an overtaxed powertrain that couldn't reliably support the vehicle's 45-ton weight. The Tiger's formidable capabilities demanded complex maintenance procedures and frequent repairs by highly trained specialists. These trade-offs might have been acceptable if German industry could produce enough vehicles and enough spare parts to maintain them. It could not, particularly as Allied bombing intensified and raw material shortages worsened. American engineers, trained in automotive mass production through decades of civilian industry experience, designed tanks that could be manufactured by the tens of thousands and maintained by mechanics with basic training using skills learned in civilian life. The Sherman powertrain used components proven in commercial service with design principles borrowed directly from automobile and truck manufacturing. Here's a detail that really shows the difference in design philosophy. The Sherman electrical system included a backup generator that could power turret traverse even when the main engine stopped. This seemed like unnecessary luxury to German designers, but it proved invaluable in combat. German tankers could only dream of such conveniences, particularly those who had experienced their turret traverse failing when engines stalled on slopes. These features didn't appear in German technical specifications because German designers had never considered them priorities compared to armor thickness and gun power. By spring 1944, Wehrmacht units on all fronts reported increasing mechanical problems as manufacturing quality degraded and spare parts became increasingly scarce. Panthers required transport by rail for movements exceeding 100 kilometers because their final drives couldn't survive sustained road marches. Field commands issued explicit orders restricting Panther movement to preserve vehicles for actual combat rather than losing them to mechanical failure during approach marches. The Burge Panther recovery vehicle, built on a Panther chassis specifically to recover disabled Panthers, shared the same reliability problems as the tank it was supposed to recover. German commanders faced a grim reality where mechanical failures eliminated more tanks than enemy action. Some units reported that 70% of tank losses were due to breakdowns rather than combat damage. Let that number sink in. 7 out of every 10 tanks lost were lost to mechanical failure, not to enemy fire. Meanwhile, Sherman production continued at unprecedented rates that German industry could never match. American factories produced 49,324 Sherman tanks during the war. That's more than all German tank production of all types combined. British Commonwealth forces received thousands through Lend-Lease. The Soviet Union received over 4,000 diesel variants. Chinese forces in Burma used Shermans to devastating effect against Japanese armor. Every theater where Shermans served confirmed what Kummersdorf testing had revealed. Properly maintained Shermans kept running under conditions that would disable or destroy German tanks. German tank crews who captured and used Shermans universally praised their automotive excellence. Reports from the Eastern Front noted that German mechanics found even the complex Chrysler A57 multibank engine, with its 5 separate engine blocks, easier to troubleshoot than German tank engines that required specialized knowledge and equipment. The Ford GAA V8, which Allied crews praised for exceptional reliability and power output, seemed remarkably dependable to German mechanics accustomed to Maybach engines that required constant adjustment of valve clearances, ignition timing, and carburetor settings. The General Motors twin diesel, which the U.S. Army had actually rejected as less reliable than gasoline engines and relegated to Lend-Lease production for Allies, far exceeded the performance and reliability of any diesel engine German industry had produced for tank applications. Think about that. An engine American engineers considered not quite good enough for their own use was still better than the best diesel Germany could build. The Sherman's generous design margins provided another advantage German engineers came to appreciate. The basic transmission and final drive components originally specified for the 30-ton M4 with 400 horsepower required no major modification to handle the 42-ton M4A3E2 jumbo assault tank with its significantly increased armor protection. The same components that powered standard Shermans successfully transmitted 650 horsepower from experimental engines without failure or need for reinforcement. German engineers tended to calculate such overbuilding as waste. They saw excess capacity that increased production cost and used scarce materials without immediate benefit. American engineers understood that margins provided growth potential for future upgrades and battlefield reliability that made the extra investment worthwhile over the vehicle's service life. This was another example of different design philosophies leading to very different outcomes. By summer 1944, German tank commanders facing the Allied invasion in Normandy knew their technical disadvantages extended far beyond individual tank capabilities. American artillery superiority, devastating close air support, and overwhelming logistical capacity combined to overwhelm German forces regardless of tank specifications or tactical skill. But the Sherman's reliability meant American armored units could sustain continuous operations that German panzer divisions simply could not match. American tank battalions could launch attacks, sustain combat operations, conduct pursuits, and immediately prepare for the next operation without extensive maintenance halts. German panzer divisions had to carefully husband their limited operational vehicles, calculating that every movement consumed precious remaining component life and brought mechanical failure closer. The difference in operational availability determined which force could maintain offensive pressure and which had to carefully ration its limited combat power. German use of captured Shermans in combat operations provided final proof of American automotive superiority from the German perspective. The 150th Panzer Brigade, formed specifically for infiltration operations during the Battle of the Bulge in December 1944, attempted to obtain captured American vehicles to disguise their operations. German planners wanted Shermans specifically because of their reputation for reliability. However, the brigade received only 2 Sherman tanks, and only one proved serviceable enough for operations. That serviceable Sherman never actually saw combat due to massive traffic jams that prevented the infiltration operation from achieving its objectives. But the fact that German planners specifically requested Shermans for an operation requiring vehicles to function without breakdowns while operating behind enemy lines says everything. Only American equipment offered reasonable chances of success. German tanks, even when fully operational, couldn't guarantee the sustained performance such missions required. January 23, 1945 brought the final official admission of German automotive failure. A meeting of the Panzer Commission produced a report documenting catastrophic final drive failures across all German tank types. The findings were devastating. Prior to the 1945 Eastern Offensive, there were 500 defective final drives in the Panzer IV, 370 in the Panther, and roughly 100 in the Tiger. Additionally, approximately 200 failures had been reported in the Hetzer tank destroyer based on the Czech 38-ton chassis. General Wolfgang Thomel, who served as Chief of Staff of the Inspector General of Panzer Troops under Guderian, explained the operational impact in stark terms. In such circumstances, orderly utilization of tanks was simply impossible. The troops lost confidence in their vehicles and in some situations abandoned whole vehicles just because of final drive problems, fearing they would be stranded and captured. German tanks, built to intimidate through impressive technical specifications, failed in the most fundamental requirement of armored vehicles: mechanical reliability sufficient to reach the battlefield and complete missions. Kummersdorf testing facility prepared for evacuation in early 1945 as Soviet forces advanced relentlessly toward Berlin. Engineers frantically packed testing data and shipped documentation to facilities farther west, hoping to preserve technical intelligence for post-war analysis. Some of the captured tanks, including at least 2 Shermans, were pressed into improvised service with combat units desperately defending the approaches to Berlin. These vehicles fought alongside German designs in the final desperate battles, providing one last comparison under actual combat conditions. The Shermans continued operating until destroyed by enemy fire or abandoned when fuel supplies ran out. The German tanks, including Panthers and the few remaining Tigers, broke down from mechanical failures at rates that shocked even experienced crews who were accustomed to poor reliability. The story of War Daddy II and the dozens of other Shermans tested at Kummersdorf represents one of the great industrial disparities of World War II. German engineers working within an industrial system that prioritized theoretical perfection over practical utility produced tanks that looked impressive on paper but failed in sustained field operations. American engineers applying decades of automotive manufacturing experience to military requirements produced tanks that lacked technical sophistication in many areas but worked reliably under conditions that defeated German equipment. In armored warfare, as in most military operations, the weapon that functions when needed beats the weapon that might be theoretically superior if it could reach the battlefield and complete its mission. This isn't a complicated concept, but it's one the Germans struggled to accept. Post-war analysis by American and British intelligence organizations confirmed what German testing at Kummersdorf had revealed. Systematic examination of destroyed German tanks found mechanical failures as common as combat damage as causes of loss. Final drives broken from stress. Transmissions seized from inadequate lubrication or operator error. Engines burned out from overheating or oil starvation. The German obsession with individual vehicle superiority and impressive specifications had blinded them to the critical importance of reliability and maintainability. They built tanks that no conscript mechanic could maintain without extensive specialized training, powered by engines that demanded constant expert attention from skilled technicians, supported by a logistics system that collapsed under the accumulated strain of supplying countless unique parts to scattered units. The lessons learned through testing at Kummersdorf directly influenced German tank design thinking in the post-war Bundeswehr of West Germany. When the Federal Republic began developing the Leopard 1 main battle tank in the 1950s, designers consciously emphasized reliability and maintainability over pure performance specifications. They studied American automotive engineering principles and deliberately applied them to military vehicle development. The resulting Leopard 1 tank incorporated many design philosophies that had made the Sherman successful. Robust powertrain with substantial design margins. Easy maintenance requiring minimal specialized tools. Standardized components enabling rapid field repairs. Growth potential allowing future upgrades without complete redesign. The Leopard 1 became one of the most successful tank designs of the Cold War era, serving with numerous armies and remaining in production for decades. German engineers had finally learned the lessons that Kummersdorf testing had tried to teach them 15 years earlier. The captured Shermans at Kummersdorf, including War Daddy 2 with its distinctive name still painted on the hull, represented far more than enemy equipment brought home for technical examination. They were tangible proof that industrial maturity and sound engineering principles, based on practical experience, mattered more than theoretical technical innovation pursued without regard to manufacturing reality. German tank designers pursued advanced specifications because they believed superior technology could overcome material disadvantages and numerical inferiority. They were wrong. American tank designers built reliable vehicles because they understood through hard experience that logistics, maintenance capability, and sustained operational availability determined victory in modern mechanized warfare. They were right, and their approach proved decisive. The reliability gap between Sherman and German tanks influenced not just tactical armored warfare but fundamentally shaped broader understanding of military industrial capacity and its decisive role in modern conflict. Germany entered World War II with technical advantages in many weapon systems, possessing scientific knowledge and engineering expertise that exceeded most opponents. However, Germany lacked the industrial depth and manufacturing sophistication to maintain those advantages through sustained mass production while simultaneously fighting enemies on multiple fronts. The United States entered the war with weapons that were less technically sophisticated in many respects but possessed industrial capacity to manufacture them in overwhelming quantities while continuously improving quality, reliability, and performance based on combat feedback. This industrial approach, perfectly exemplified by Sherman tank design and production, proved far more effective than German technical sophistication applied to small-scale production. The United States produced nearly as many Sherman tanks as Germany produced tanks of all types combined, while also producing enormous quantities of every other weapon type, supplying allies through Lend-Lease, and maintaining the highest standard of living among all combatant nations. This economic performance, impossible for Germany to match even before strategic bombing intensified, decided the war's outcome as certainly as any battle. The mathematics were simple and brutally clear when examined objectively. A Sherman with a 75mm gun that reliably reached the battlefield and fought effectively was infinitely more valuable than a Panther with a superior gun that broke down before engaging the enemy or required 3 days of maintenance for every day of operations. A tank battalion with 80% of its vehicles operational could execute missions that a battalion with 40% operational vehicles simply could not attempt. Reliability wasn't just a convenience factor or secondary consideration. It was the foundation of operational effectiveness, determining whether armored units could execute their assigned missions. German tanks consistently failed this fundamental test throughout the war. American tanks consistently passed it. Kummersdorf testing had proven this beyond any reasonable doubt by mid-1943, even as German commanders continued deploying Panthers and Tigers that looked fearsome and possessed impressive specifications but couldn't be relied upon to function when needed most. The Sherman tank didn't win World War II through technical superiority in firepower or armor protection. It won through industrial superiority expressed as mechanical reliability, consistent availability, and ease of maintenance. German engineers at Kummersdorf understood this by mid-1943 based on their exhaustive testing. They wrote detailed reports documenting their findings. They tested the evidence repeatedly with scientific rigor. They reached correct conclusions about American advantages. But understanding a problem and solving it are fundamentally different challenges. German industry lacked capacity to retool production around reliability principles while simultaneously fighting a losing war on multiple fronts against enemies with superior resources. American industry had built reliability into its civilian automotive sector over decades of commercial competition and simply extended those mature principles to military production with remarkable success. War Daddy 2, that single Sherman tank captured in Tunisia and tested exhaustively at Kummersdorf for months, told the entire story through its mechanical reliability and consistent performance. Every kilometer it drove without failure was evidence that German tank design had taken a fundamentally wrong path by prioritizing specifications over reliability. Every test that demonstrated American automotive excellence was proof that industrial maturity and practical manufacturing experience mattered more than theoretical performance calculations. Every comparison between Sherman and German tank reliability proved that Americans had solved problems German engineers didn't realize they needed to solve. The tank itself was unremarkable in many ways, just one of 49,000 produced. What it represented was devastating to German confidence, proof that Germany had already lost the industrial war even as fighting continued, and that American productive capacity could not be matched regardless of German technical sophistication or tactical skill. This story matters today because it teaches us something fundamental about engineering, manufacturing, and military effectiveness. Impressive specifications on paper mean nothing if equipment can't function reliably under actual operating conditions. Theoretical perfection means nothing if it can't be manufactured at scale. Advanced technology means nothing if it can't be maintained by ordinary soldiers under combat conditions. The Sherman succeeded not because it was the most advanced tank of World War II. It succeeded because American engineers understood that good enough, produced in massive quantities, maintained easily, and operating reliably, beats theoretically perfect every single time. That lesson applies to far more than just tanks. It applies to any situation where equipment needs to function in the real world rather than in controlled laboratory conditions. German engineers at Kummersdorf learned this lesson the hard way, watching an ordinary American tank do things their advanced German tanks could not do. They documented their findings. They reported their conclusions. But by the time they understood what they were facing, it was already too late to change course. The industrial war was already decided. All that remained was for the fighting to catch up with the inevitable conclusion. If you found this story fascinating, make sure to subscribe to the channel. Hit that like button and leave a comment sharing your thoughts on this incredible piece of history. We've got plenty more compelling stories like this one coming your way.